Hey everyone, and welcome. Today, we're going to crack the secret code of the entire universe. And that code is units and measurements. Now, I know what you're thinking, but this isn't just some boring chapter in a textbook. This is the actual language of physics. It's how we describe literally everything, from the tiniest particles to the most massive galaxies. So you ready? Let's dive right in.
Okay, just imagine for a second you're baking a cake, and the recipe says add 10 sugar. You'd be totally stuck, right? Is that 10 spoonfuls, 10 grams, 10 whole cubes of sugar? Without that little bit of extra info, the unit, the number 10 is absolutely completely useless. And your cake? Well, it's probably going to be a disaster. Well, physics is exactly the same. A number all by itself means nothing. It's the unit that brings it to life.
And that brings us to our first huge idea, the physical quantity. Basically, it's anything in the universe we can actually measure. You know, things like how long something is, how hot it is, or how fast it's moving. And every single physical quantity has two parts, always. A number, which we'll call n, and a unit, u. So if I say my desk is 2 meters long, 2 is the number, meters is the unit. And you've got to have both, no exceptions.
Now here's where it gets interesting. When you look at all the different units we use in physics, it turns out they're not all created equal. There's a sort of hierarchy. Some units are the absolute foundation, the bedrock that everything else is built on. Let's break down these two types, fundamental and derived.
The best way to think about it is like an alphabet. The fundamental units are the letters of physics. There's only a few of them, just 7 in fact, and we just have to accept them for what they are. You can't break them down any further. But with those 7 letters, you can build an entire language. All the other things we measure, velocity, force, energy, those are the words. We call them derived units. And every single one is just a clever mix of those fundamental letters.
So if we're going to have a language for physics, it makes sense that everybody should be using the same alphabet, right? I mean, imagine scientists trying to work together, but one's using 26 letters and the other is using 30. It would be total chaos. And that's exactly why the world's scientists all agreed on one standard system, the Système International, or, the SI system. This is our global rulebook.
And here they are, the Magnificent 7. Believe it or not, these 7 fundamental quantities are all we need to describe pretty much everything. First, you've got your big 3 for mechanics: length in meters, mass in kilograms, and time in seconds. Then you've got electric current in amperes, temperature in Kelvin, amount of substance in moles, super important for chemistry, and lastly, luminous intensity in candela. Seriously, every other unit you'll ever see is just some combination of these guys. So let's see how this actually works. Area? That's just length times length, so you get meters squared. Easy. Velocity? Well, that's how far you go over a certain time, so it's length divided by time, meters per second. But what about something beefier, like force? We all know F equals ma, right? Force is mass times acceleration. Mass is kilograms, acceleration is meters per second squared, so you just smash them together and you get the unit for force. Kilogram meters per second squared. See? We're literally just building bigger words from our basic alphabet. Okay, so we've learned the alphabet and we've learned how to make some words. Now, I'm going to give you a superpower. It's the grammar of physics, and it's called dimensional analysis. And here's why it's so amazing. The laws of physics don't care if you use meters or feet or kilograms or pounds. The real physics underneath has to stay the same, and dimensional analysis is the tool that lets us check that. It's our secret weapon.
So what's the secret behind this superpower? It's the idea that every single physical quantity has its own unique signature, a kind of dimensional formula. This isn't about the unit, like meters or seconds, but the type of thing it is. Is it a length? Is it a mass? A time? Or some combination? This formula boils any quantity down to its most basic, fundamental roots. It's like finding the true origin of a word. Now, to write these formulas, we use these simple symbols, and this is super important. These are dimensions, not units. Any mass at all, kilograms, grams, whatever, has the dimension of mass, which we write as a capital M in brackets. Any length is L. Any time is T. Temperature is K, and electric current is A. But honestly, for most of what we do in mechanics, you just need to worry about the big 3, M, L, and T.
So how do you actually do this? Let's take our old friend force. It's a simple 4-step recipe. Step 1, start with the formula you know. Force equals mass times acceleration. Step 2, think about the basic units. That's kilograms for mass and meters per second squared for acceleration. Step 3, swap the units for the dimension symbols.
A kilogram is a mass, so it becomes m. A meter is a length, L. A second is a time, T. So now we have m times L over T squared. And for the final step, step 4, we just clean it up. We write it all on one line, so anything on the bottom comes up to the top with a negative power. And there you have it. The dimensional formula for force is m1 L1 T minus 2.
And trust me, you have to know that one. There's this old joke that goes around with physics students that if you ever want to get married, your future father-in-law won't ask about your salary. No, he's going to ask for the dimensional formula of force. It's silly, I know, but it really shows you how fundamental this is. It's like the hello world of dimensional analysis, a real rite of passage.
All right, theory time is over. We've learned the code, now let's actually put it to work. Because this isn't just some neat party trick to impress your friends. Dimensional analysis is an incredibly powerful tool for solving real problems, especially when you need to switch between different systems of units.
So let's start with a core idea. Let me ask you something. We know every quantity is a number n times a unit u. So what happens if I decide to measure a table using centimeters instead of meters? Well, the unit, the centimeter, is way smaller than the meter, right? It's 100 times smaller. So to measure the same exact length, the number I write down has to get 100 times bigger. One goes down, the other has to go up. It's an inverse relationship.
And that simple idea shows us a huge principle in physics. For any physical measurement, the number times the unit is always constant. The actual length of the table doesn't change just because you changed your ruler. We can write this as a super useful formula. N1U1 equals N2U2. Think about it. 3 meters is the exact same thing as 300 centimeters. The product is the same. This little formula, it's the key to all unit conversions.
Okay, time for the main event. Let's fire up our superpower and tackle a really tough problem. We need to convert 1 joule of energy, that's the standard unit, into a brand new, totally made-up system. In this weird new system, the unit of mass isn't a kilogram, it's alpha kilograms. The unit of length is beta meters, and the unit of time is gamma seconds. How on earth are we supposed to figure this out?
We're going to use this, the master formula. And I know, that looks like a lot. It looks really intimidating. But trust me, it's just a recipe. N1 is our starting number, which is 1. And 2 is the new number we're hunting for. And all that stuff in the brackets, those are just the ratios of the old units to the new units for mass, length, and time. The only real secret here is figuring out what those little exponents, x, y, and z, are supposed to be.
And this is where our superpower kicks in. Step 1. Find the dimensional formula for whatever we're converting. In this case, it's energy. Let's do it real quick. Energy is work, and work is force times distance. We already found the dimensions for force, mLT -2. Distance is just a length, L. So we multiply them together, and we get m1 L2T -2. And boom, just like that, we have our secret numbers. The power of mass, m, is 1, so x is 1. The power of length, L, is 2, so y is 2. And the power of time, t, is -2, so z is -2. This first step gives us the keys to the whole problem. Okay, the hard part's over. Now it's just plug and chug. Step 2 is easy. We just plug in all the numbers we know. Our starting number, N1, is 1. Our first system, System 1, is just the normal SI system, so M1 is 1 kilogram, L1 is 1 meter, and T1 is 1 second. Our new system, System 2, is that weird custom one, so M2 is alpha kilograms, L2 is beta meters, and T2 is gamma seconds. We just slot all of that into the formula, along with the exponents we just found. X is 1, Y is 2, and Z is -2. And now for the really satisfying part. Let's watch the magic happen. When we simplify, the kg cancels with kg, m cancels with m, s cancels with s. All the units just vanish. We're left with 1 over alpha to the power of 1, 1 over beta to the power of 2, and 1 over gamma to the power of -2. Now remember your exponent rules. 1 over alpha to the 1 is just alpha to the -1. 1 over beta squared is beta to the -2. And here's the tricky one. 1 over gamma to the -2, well, the negative exponent flips it, so it becomes gamma squared. And that's it. That's our answer. We did it. The new number is alpha to the -1, beta to the -2, gamma squared.
So, converting units is cool, but that's not even a half of it. If dimensions are really the grammar of physics, that means you can use them to check if any physics equation is grammatically correct. An equation only works if the dimensions on both sides of the equal sign are exactly the same. It's like spell checking your math. So here's a final thought to leave you with. What other formulas could you test with this? Could you maybe even derive an equation from scratch just by knowing what it depends on? That, right there, is the true power of this secret code.